January 13, F322, question 4. This is your equilibrium question. Here you've got hydrogen reacting with carbon dioxide to form methanol and water. Key to this one is telling you from the outset that you've got 49 kilojoules released when 3 moles of H2 react completely. So the first thing I'm thinking in this question is, right, 3 moles of H2 reacting, 49 kilojoules. How much for 1 mole then? Because that's going to be useful conversion. So for 1 mole, I'm just going to put this on the side for now, we've got 49 over 3, which equals, and I've lost my cursor again, which is really frustrating, 16.3 kilojoules. So if I'm reacting 1 mole, and I'm doing that because I think I'm going to need a conversion. Here in my first question then, I've got 1,000 decimeters cubed of hydrogen, measured at room temperature and pressure. Now, that is important because it tells me that I'm good to use one of my mole equations, because it's saying calculate the energy released when 1,000 decimeters cubed of hydrogen is reacted. So the energy released, it's told me I've got 49 kilojoules for 3 moles, or for 1 mole of hydrogen being reacted, I've got 16.3 kilojoules. So I need to work out a number of moles. I've got a volume. So we've got then N equals V over 24 equals 1,000 over 24, which is equal to 41.7 moles. Now, that's my number of moles. I'm simply now going to times that by 49 over 3, which gives me 681.1. Now, what I'm not going to do in this question is be a muppet and not read that I've got 3 significant figures. I'll be a muppet because I can't see my cursor, and I'll scribble over there when it should be, there you go, there, 3 significant figures. So my final answer, somewhere down here, 681. So that's the first part of the question. Then, to go on, you've got to draw an enthalpy profile diagram, and this is certainly going to be interesting. Okay, so here, part B, complete the enthalpy profile diagram for the forward reaction. Put my label down here, and in fact, why have I put it down there? I've got to go back up and check, haven't we? Why is it that I know that this is an endothermic? Well, how do I know it's endothermic or exothermic? Here we've got energy released. So in this reaction, 49 kilojoules of energy are released. So because it's released, I know it's an exothermic reaction, so my delta H will be negative, so I have to go down in my diagram. So here I've got then my line at the bottom. I have to write in what my products are. That's going to be part of the mark scheme. So CH3OH plus H2O. I've got to make sure that that's balanced as the mass as the equation up the top there, and it is. I've just got 1 mole of each of those. Then I'm going to take my loop or hump, I'm going to send it down to the bottom. Now, I'm going to have to apologise for a poor drawing of this, but essentially, you've then got to pop on, label the activation energy and the enthalpy change. So I've put my reactants down the bottom, I've got it going the right way. Down here I've got my dotted line. I want to try and put my activation energy to the top of my peak there, which I've done there in that box. Right, it's staying. Now, activation energy is all about the minimum energy to break bonds. So breaking bonds, you've got to put energy in. Energy is being absorbed to break the bonds. So this arrowhead must be pointing upwards. And I'm going to label that very, very clearly EA. And EA is good enough because it said label the activation energy EA. And the enthalpy change, so the enthalpy change here, different colour. The enthalpy change is from here to there. So I'm going to put that in clearly, get your arrow to the line. And here again, delta H. I'll put a negative in as a reminder. It's negative, so my arrow pointing down. And then that is all you need in there for that one. You get 1 mark for correctly labeling the activation energy, 1 mark for correctly labeling the enthalpy change with the arrows in the right direction. Put your products on. The axes check are already labeled. Now, as is typical with these questions, the next part asks, what is the enthalpy change of the reverse reaction? So it wants you to look at going backwards. And going backwards, the enthalpy change is from here, at the same level of enthalpy of the 2, there. That's the reverse change. So all you're doing is changing the sign of this value. And you were given that value as being, you go back to the top of the question there, you're given that value as being 49. That's our original 49. In fact, I'll write that in there now. So this was 49, and in fact minus 49 because energy was being released. So this reverse arrow now is simply the reverse of that plus 49. Then the question beyond, and I'm going to stay with the diagram now and I'll fill those in a minute. The question beyond on part D then asks, having given you a piece of information, it tells you that the activation energy for the forward reaction in part D, which is over the page, it says that the activation energy for the forward reaction is plus 225. And it says, using this information, estimate the activation energy of the reverse reaction. So the reverse reaction is simply, let's use a different colour here. What have we got? Black. The reverse reaction, you've got the plus 49 for the enthalpy change, but in total, your activation energy, if we're going backwards, it's got to go, your initial activation energy has got to go all the way to the top of the peak there, like that. So that is my EA. For the reverse. So it's 49 plus 225. So 49 plus 225 equals, for part D, 274. Remember, activation energy is always positive because it is about breaking bonds. You've got to put energy in. So I'll just fill those in as the answers then. Here then, the reverse reaction, you're changing the sign, so you've got plus 49, and over the page you've got an activation energy of plus 274, explained from the graph. Now we've got to look at the position of equilibrium. So in part E, the temperature of the equilibrium mixture is increased. So we've got temperature increased. I thought it was going to give me a highlighter, but there you go. So temperature increased. So describe and explain what happens to the position of equilibrium. And I've put here the equation for us so we can just refer to this now. The key part of this is that our delta H from previously in the question is equal to minus 49. The key bit being here, the minus, which means that the forward reaction is exothermic. Now from Le Chatelier's principle, we know that a dynamic equilibrium will resist changes imposed on it. So it'll try and minimize the change. So here we've got an increase in temperature, and we've got an exothermic reaction in the forwards direction, so giving out heat. What we want then to minimize the change is to absorb the temperature, and so this equilibrium will shift left to the endothermic direction and will absorb that temperature that's been increased. So for our 2 marks that we've got here, we will need to state first of all favours the backwards reaction. So therefore which way am I going? Backwards is left, so equilibrium shifts left. 2 marks. Or is it? What have I forgotten? Favours the backwards what type of reaction? It favours the backwards endothermic reaction. Equilibrium shifts left. I suppose I should make my full sentences. The equilibrium, or the system, favours the backwards endothermic reaction. Equilibrium shifts left. So how about that? Then similar kind of question, keeping that equation there. We've got this time that the pressure is changing. Total pressure of the mixture decreased. So that the pressure is decreasing. The equilibrium, to minimize the change, will want to try and do the reverse, so increase the pressure. Which side has more moles and so would increase the pressure because it will have a greater number of different molecules in the same volume? That's the left side, and we've got to say because it has a greater number of moles. So the equilibrium will shift left as there are more gaseous moles on the left. course, you could use the reverse argument. Equilibrium will shift to the left as there are fewer gaseous moles on the right. Final question here is a green chemistry question, really. The reaction, which is our methanol production reaction, uses a solid catalyst. The catalyst functions in a similar way to the catalyst used in catalytic converters. So we've got our 3 stages essentially that they're asking us for how a catalytic converter helps convert pollutants into harmless CO2. So here we'll have first stage. It's that key word in the first stage, isn't there? Could be specific here, so I'll say H2. I should pause this, shouldn't I? H2 and CO2 will be, keyword, absorbed onto the surface. So as long as you've got that, they will be absorbed onto the surface. Notice how I'm making it specific to this particular question. Always a good thing to do, just in case they're marking for that. Then, what happens when they're absorbed onto the surface? Why is this catalyst producing a better route for the reaction? It must be that this weakens the bonds. So it's going to be easier for the reactants to form products because their bonds have been weakened. This weakens the bonds of the reactants, if you're going to be precise. Then, finally, the products, which in this case is CO, no it's not, it's water and methanol. The products H2O and methanol are desorbed. That's the other key word. And that's fine. That's all you need. Adsorbed, bonds weakened, desorbed. Just make it specific to the particular question you're answering.